Hello everyone. So today we will look at the application of thermal analysis, right, to study construction materials, right. How can we use these techniques to understand the construction materials better, right. That will be the goal of today's lecture. Okay. So if you look at DTA of aggregates, right. So we can use this differential thermal analysis to probe the aggregates we use to make concrete, for an example, right. But you see here you see DTA curves for different types of aggregates, starting from limestone, siliceous sand, basalt, calcareous, quartz sand. These are the common aggregates used in concrete. How these respond to DTA, right. That is what. So basically what you see here, you see this transformation, quartz transformation you are able to see. So quartz transforms from alpha to beta form. Okay, that transformation occurs at around 575 degrees Celsius, right. Obviously, so yeah, so these are the peaks which can be attributed to this transformation of quartz, and makes sense because you are talking about siliceous sand and quartz sand. So it has lot of quartz, so that will transform. So DTA can be used to study that. Also you see these peaks in limestone, right, and even calcareous quartz sand. This is because of CaCO3 dissociation. You have a calcite, calcium carbonate. So calcium carbonate will decompose like this, right. So this is a decomposition. So you see these endothermic peaks. Endothermic means you need heat, right. So basically we can use DTA to understand the aggregates. That is the idea.
So coarse aggregate we can also determine this?
Yes.
For that sample preparation we have to make a powder for
Right, right. You will have to make a small powder, basically few milligrams.
yeah.
Okay. This is the DTA curve of kaolinite. Kaolinite is type of clay, right, commonly found. So what happens when you increase the temperature? So you see x-axis is temperature. Do not get confused with 240, it is 2 times 100, 200, 400, 600, 800, 1000 degrees Celsius temperature, right. So you basically, if you look at the DTA curve up to 1000 degrees Celsius, right, we are talking about see 1100 to 1200 degrees Celsius. What happens, you see small peak here, endothermic peak, which is because of loss of physically adsorbed water. It will always have some water. When you lose that water, you see this peak, right. The second peak, major peak, is because of loss of structural water. Structure, the water which is present in this its structure gives you this peak, endotherm, it is a endothermic peak at around 550, 650 degrees C. So you are losing structurally bound water. And then you have this peak at around 980 degrees C, it is an exothermic peak. See the difference, endothermic and exothermic. Here you are releasing heat, right. It is because of some crystallization, you know, we are not going in detail. It is like because your clay is made of aluminum and silicon, right. So there is this spinal crystallization which occurs at around this. So basically we can use differential thermal analysis to understand the clay, and can give us what kind of transformations can occur when you heat the clay to really high temperatures. Here is an example of DTA curve for white cement clinker raw mix. We are not talking about cement paste, it is a white cement, and we are looking at this endotherm. So sorry, so here is the DTA curve. So you see endotherm is in this direction, exotherm. Usually when you plot DTA, you will have to decide which direction is exotherm, right. Usually it is drawn this way, right. So you know the this peak, the first peak around 1290 degrees C, it is an exothermic peak due to belite formation. Belite is forming, right. Belite forms at around that temperature. So you can see that is given as exothermic peak. Then this is the endotherm due to melting, right. Now if you further heat it up, then melting will start, right. So you see this endothermic peak, right. These are the major things. Small this peak is because of the again transition. Now your beta has different polymorphic forms. So alpha prime H, when it transforms to alpha, gives you this. So these are some signatures you can get through DTA. Now if you look at the DTA curves for Portland cement paste, right, you mix cement with water and then make paste, and also starting with the unhydrated part, right. You see how the DTA curves change, right. 15 minutes, 1 hour, 16 hours, 24 hours, 3 day, 5 day, 7 day. See first of all what is the difference. You see some changes, right, in the DTA curve, some things are forming, that tells you okay, the reaction is taking place, new phases are being formed. So from here you can identify what kind of phase is precipitating, right. Starting with, you see first of all at 485, around 500, see major peaks, right. Now at 7 day you have a very prominent peak, it is because of Portlandite. We all know when cement hydrates you form calcium silicate hydrate and calcium hydroxide. So prominently you see this peak, significant, tells you, and it is around 500 degrees Celsius for an example. So this tells you that new phase has formed, which is not present here in unhydrated, or very low amount, right, and at later age significant amount of this phase is there. Now you see a lot of things are happening at early age in that from 100 to 140. So there are a lot of phases. So first of all, this Ettringite, or you can call Ettringite also, Ettringite is formed in this range. So 135 to 140 degrees Celsius, that range is because of Ettringite. It also you can see that it overlaps with CSH, calcium silicate hydrate, because calcium silicate hydrate will also lose water at that range. So you see at the later age, let us see 3 day, 5 day, 7 day, you have a peak around, so you see this peak, right, 120, 125 can be primarily due to CSH, like loss of water from CSH, right. And then you also have a AFM phase, your AFT phase like Ettringite gets transformed to monosulfate. If you, for this just refer to any standard book on cement hydration, we are not going detail, but AFM phase phases are formed. So you see at around 185 to 200 degrees C, right, this is because of AFM phases, right. So see from DTA curve you get lot of information what kind of phases are formed, right. Yeah, so it also poses challenge, sometimes there might be overlap, right. So like you can see here Ettringite, CSH, there is quite a bit of overlap, right. So if you really want to identify what kind of phase you have, you will have to try different other techniques, right. But idea is the DTA curve can be used to get some insight, like the kind of changes the material undergoes when it is undergoing temperature change. Okay, DTA curve for cured calcium aluminate cement, CAC, right. Calcium aluminate cement is also different, it is not Portland cement, right. It has calcium aluminate which hydrates, forms calcium aluminate hydrate, right, Ca. We know that we talked about the conversion, that is what happens at high temperature. So you can see here these are the DTA curves of cured calcium aluminate cement, right, and cured means cured at different temperature, 20 degrees Celsius, 30 degrees Celsius, 38 degrees Celsius. So we talked about the conversion. So you can see here in 38 degrees C cured sample you see C3AH6. This is the conversion happens, obviously it takes time, usually it may take time, but using DTA we can identify, right, what kind of phases are formed, right. So when you cure your CAC or calcium aluminate cement at 38 degrees Celsius, you see presence of C3AH6, and also you see gamma AS3, it is nothing but crystalline form of AS3 or gypsite we call, right. Initially you have amorphous gel. So various phases in calcium aluminate cement can be identified. Coming back to now DSC, right, now we are talking about heat, right. So DSC curve of hydrated OPC. So DTA DSC curves will look similar, only thing is like y axis will be different. In DTA you will have temperature as y axis, in DSC you will have heat flow. So again you get the similar information, see here. So here we have two different, so let us see two different samples. One is the solid line refers to 10-day old sample, solid line. The dashed line refers to 16 days whole sample, right. But you see similar peaks. So, what you see peak 1 primarily is because of loss, water loss from CSH, calcium silicate hydrate, which occurs at around 100, right, this regime. Okay. Then comes second peak, 2 major peaks. Let us look at second peak is around again 450, 500, right. This is because of loss of water from Portlandite, dehydroxylation of calcium hydroxide. What does that mean? Calcium hydroxide will come back to it again, right. So, this is very powerful. So, we can see that change. And also third peak, obviously it is small, it depends on the amount of calcium carbonate you have system. If you have a significant amount of calcium carbonate, then you will see significant peak here, but here you see small peak, but that tells you about the decomposition of calcium carbonate, right. You have some other smaller peaks you see here because of eternite, ion substituted eternite, and also some solid solution, right. So, but idea is major peaks you are able to identify easily, okay. Yeah.
So how do you understand that all these peaks correspond to a particular?
Right, that is good question. How do we understand? You have to look at, so you will have to do test on like pure phases. So, calcium hydroxide for an example, when you just take calcium hydroxide and do test, you will get a signature. So, then it is like a matching, you know, when you do peak matching for your X-ray diffraction. There is a database where we know the information. So, calcium hydroxide, when you heat it up, it will start decomposing only at 450 around degrees Celsius. I have a slide on that, so it will be more clear, right. So, so in Portland cement system, peak around 450 degrees Celsius tells you that it is a Portlandite, because that is where the Portlandite calcium hydroxide dehydroxylates, okay. Similarly, calcium carbonate, that occurs at later stage at around 600, 700 degrees Celsius, you will start seeing that decomposition of calcium carbonate into calcium oxide and carbon dioxide, okay. That is why again the point is to look at multiple techniques, you know, to get better idea. So, here is you see let us look at the application of DSC in assessing durability. So, on the left side you have XRD plot, right. XRD tells you what kind of phases you have, right. So, here you see pattern 1 and 2. One is basically it is OPC with 35% limestone paste stored in 1.8% magnesium sulphate and 1.8% sodium sulphate for 224 days, right. So, we are talking about a kind of sulphate attack. So, in this case, but we are talking about thomosite type of sulphate attack. So, you see the formation of T, thomosite here denoted as T, right. It is very close to eternite. We discussed that in XRD, right. So, you have this X-ray diffraction pattern from 2 different places, right. So, so one is pattern 1 is expanded corner of prism. So, apparently what they did, they exposed these prisms to this solution for longer time, then they took sample, right. So, the expanded portion, they took sample from expanded portion, the corner of prism, and did XRD. So, you found this chalky surface deposit, there must be some surface deposit, and they did XRD on that. So, you have a different X-ray diffraction pattern. But let us look at this. So, you are seeing the formation of thomosite, that can also be confirmed here. We will look at the DSC curve, right. DSC curve will give you basically at here you see 2 major peaks, right. One is because of thomosite and one is because of gypsum. If you look at the XRD, you see formation of both thomosite and gypsum, right. And there is another signature here, it is because of brucite, magnesium hydroxide, right. So, when you combine techniques, that give you more insight, right. But one technique can also be used to identify the changes, right, or phase formation. Okay. Now, we will look at thermogravimetry. It is commonly used because we can quantify it. Basically, we can find out the phases, phase amount like calcium hydroxide, calcium carbonate easily. So, it is commonly used. You will see lot of papers on this, right. So, how does a TGA curve of Portland cement paste look like, right. So, TG is basically measuring the mass loss, right, mass change with temperature. So, you always see on x axis you have a temperature, y axis you have a relative weight. When you start your experiments, nothing has lost, right. So, it is 100%, right, that is how you will see lot of times so 100% means no, nothing has been lost. So, when you start heating the sample, you see mass loss. So, this is your mass loss curve, right. So, you see by the end of 950, when you reach 950 degrees Celsius, in this case you almost lost 20% of weight. Now, your relative weight is around 80%, right, clear. Now, yesterday we talked about the importance of DTG. So, by looking at this curve, we see okay, there is something happening here, but visually we can get more information when you take derivative. So, derivative means you are using the same data, no new information, but you are plotting the slope, right. So, derivative plot. So, you see here derivative plot, easily you can identify there are 3 regions of significance. One is this early one region at around like 100 to 150 degrees Celsius, second is somewhere here, right, third is somewhere here, right, clear. Lot of things are happening. So, this early like around 100 degrees Celsius you start losing water, right. So, you are losing water from CSH, calcium silicate hydrate, you are losing the eternite also starts decomposing, right. You have other phases, monosulfate, monocarbonate in this case, right, because we are talking about there are 2 samples here, the one is dark one is PC like Portland cement, bright one is PC4 means Portland cement with 4% limestone. So, notice in limestone case, first of all you see this extra peak, obviously you have a more limestone, so you are going to see more loss change, more mass loss because of limestone, calcium carbonate, right. So, this is evident. Here again we come back to it, whenever you see peak at around 450, it is because of Portlandite, calcium hydroxide, because OPC will hydrate and form CSH and calcium hydroxide. But this region at around 100 to 150 degrees Celsius, you have a overlap of lot of peaks, eternite, CSH, that is why it is very hard to quantify these phases, because it could be anything, it could be CSH, it could be eternite, it could be, I mean monocarbonate and monosulfate are somewhere here, they are different, but at least there is a big overlap between calcium silicate hydrate and eternite. That is why we can clearly use this TGA to quantify calcium hydroxide where there is no overlap and calcium carbonate without an issue, right. Also we can use this TG to understand the influence of temperature. What happens when you increase the temperature from 5 degrees Celsius to 50 degrees Celsius. So, again you have here is an example of sulfate resisting Portland cement SRPC. You see lot of lines, lot of curves. Here you have unhydrated means without water, then you add water. So, what happens after 3 hours, 6 hours, 1 day, 28 days, so we are monitoring the progress of hydration. Cement will hydrate, form new phases, right. How that affects the TG curve, that is what we are looking at. So, so you see that initially there is not much mass loss, but slowly you are seeing increase in mass loss, right. Look at the legends, it is clear, because you are forming products, you are forming new phases. So, that is because of the dissociation, decomposition of the new phases, right. So, again you see 3 big regimes. In Portland cement you will see these at around 150 degrees Celsius, that will be a region. Then you have around 450 degrees Celsius Portlandite, then you have calcite 700 degrees Celsius. See, also you can notice the size, right, Portlandite peak initially it is here, then it is increasing, tells you, because it is directly related with the amount. We are monitoring, we are measuring the mass change, we are measuring the mass change. So, more mass change means more amount, right. So, you see change in the peak. So, it can tell you how the hydration is progressing, what is increasing, what is decreasing, right. So, in this case you see increase in Portlandite with time. See here also initially you see some gypsum hemihydrate, this, right, then it disappears. Obviously gypsum will react, right, with C3A and form eternite, right. So, initially you see that, but later on you see all eternite, right, and some like CSH, right. Same thing if you do at 50 degrees Celsius, the changes. One thing you will notice, if you cure your sample at high temperature, you change things. See here, if you look at the weight loss curve on the left side, if we are looking here, slow change, right. So, 3 hours you are still here, right, 6 hours you are here, right. So, slow change, but here you have a rapid change, because that is the effect of temperature. You are increasing the temperature, so you are accelerating the reaction, that gets reflected in DTG also. DTG is nothing but first order derivative of your TG curve, right. So, again similar regions can be identified, and depending on the composition, right, you have so we may have, in this case you have a monocarbonate because of maybe you have, they use a little bit of limestone in this case, right. But you have to be careful when you want to quantify eternite using TG, because the peak is overlapped with CSH, because CSH also starts losing water at around that. That is a big thing. So, you have to look at, you have to, for quantifying eternite, X-ray diffraction is a better technique, but for quantifying portlandite calcite you can easily use thermogravimetry, right, because there is no overlap. Also we can use it to assess the reactivity of fly ash. We use fly ash, right, and why do we use fly ash in concrete? Yeah, we replace cement. Why? Right. So, it is because fly ash is pozzolanic. Pozzolanic means it reacts with calcium hydroxide, right, and forms calcium silicate hydrate. See, you are getting, when cement is hydrating, right, when you add water, it gives you CSH and calcium hydroxide, CH, right. Now, somehow if you could get some silica, amorphous silica, and make it react with CH, you will form additional CSH. That is a simple thing, right. So, now it tells you like how do you assess reactivity of fly ash. If you could measure calcium hydroxide, that will tell you how reactive fly ash is, because if it is reactive, it will react with calcium hydroxide and decrease the amount. There will be, it will react faster rate, and then there will be reduction in the amount of calcium hydroxide. So, that is what you see. So, let us see here. First of all, let us look at the TG curves. So, these are, so dark lines again are for OPC, 65% OPC, 35% fly ash, and the bright ones are for 65% OPC, 30% fly ash and some limestone, 5% limestone, right. So, you see this TG like typical response, right. Now, if you plot DTG, it becomes more clear. What you see, okay, you see a region here, we are looking at the region up to 550 in this case, right, because of calcium hydroxide, and this initial region where you have a CSH, AFT, eternite, and then you have a subsequent peak AFM. Okay. What do you see difference when you do it now? This is at 28 days. When you do the same thing, when you do thermogravimetry at 140 days, you would expect your fly ash will react with calcium hydroxide and the amount of calcium hydroxide will reduce. That is what you would expect, right, because of the pozzolanic reaction. So, you see the peak, they are there is the same scale here. So, you can just compare the peaks compared to this. So, you see a reduction in the amount of CH, right. So, it tells you about the pozzolanic reaction. Now, same thing has been plotted here, CH percent means calcium hydroxide percent against the fly ash amount. So, when you have a 0% fly ash, no fly ash, you see okay, cement is hydrating, you are here, then with time it increases, right, your cement is hydrating, you have more and more calcium hydroxide formation. What is happening when you are adding fly ash, your amount of calcium hydroxide is decreasing, okay, and with time, right, this could be because of dilution also. Initially we are talking about 1 day, right. But with time what you see at 140 days, instead of here it is somewhere here, right. So, you are consuming calcium hydroxide, right. So, it is very good way to assess what you say the reactivity of pozzolans using thermogravimetry by quantifying the amount of calcium hydroxide, because that is what directly it corresponds to. Pozzolonicity means reaction between amorphous phase of your pozzolan with calcium hydroxide. Okay. So, by finding out how much calcium hydroxide is left, you can tell how much has been consumed.